In this video, we are presenting our work, Continual Model-Based Reinforcement Learning with Hypernetworks. Model-based robot learning requires continual adaptation of accurate dynamics model on new tasks. For example, the robot may need to deal with changing terrains, pick up unseen objects, or simply learn how to do a different task such as walking to climbing. Continual learning studies how to transfer knowledge for new tasks while avoiding catastrophic forgetting in neural networks. Here, we provide a brief overview of the main ideas in the literature. Expanding the capacity of neural network is a natural way to augment the network for new tasks. One example is the progressive neural networks. New neurons are added horizontally in every hidden layer and connected to all neurons in the previous layer, thereby eliminating any forgetting and improving knowledge transfer. However, the downside of this method is the significant memory and compute costs. Regularization-based methods add a regularization term to the loss function that prevents the important weights in the network from drifting, while other weights can adapt for new tasks. Elastic weight consolidation uses Laplace approximation to the exact posterior that fully incorporates all previous data. In practice, the approximation is imperfect and may still be prone to forgetting. Our work is based on a recent paper which uses Hypernetwork to regularize weight changes and reduce forgetting. Variational continual learning is a framework that uses variational inference to train the Bayesian neural networks, evolving over time. When new data arrives, it uses Bayes' rule to combine previous posterior with the likelihood on the current data. Then, the model weights are updated recursively by fitting a variational approximation to the new posterior. Lastly, the simple idea of storing and replaying a small subset of past experiences in training turns out to work surprisingly well in many benchmarks. Past data can also be used to limit the negative effect of current gradient updates on all tasks. There are also many intelligent strategies to build a course set to summarize past data. For example, using variational inference to learn inducing points in a sparse Gaussian process can be seen as course set selection. We propose HyperCRL, a task-conditional, fixed-capacity hypernetwork for representing non-stationary dynamics. First, the dynamics learning session of HyperCRL does not revisit training data from previous tasks. Our method also adapts the dynamics of new tasks while avoiding catastrophic forgetting of old ones. Here is an overview of our method. We represent the dynamics model with a simple neural network. Then, the hypernetwork generates the parameters of a target network given a learned task embedding. Using the current dynamics model, we can perform cross-entropy method to optimize the best action sequences and execute with model predictive control. The task embeddings and weight of the hypernetwork are updated with task-specific replay buffer, collecting state transition experiences from the current environment. The replay buffer resets to empty at the start of every new task. To prevent catastrophic forgetting, we regularize the output of the hypernetwork for all previous embeddings. This minimizes changes in the target network, which represents the dynamics. The overall loss is the sum of the dynamics error of the current task plus the regularization term. In the first simulation experiment in Surreal Robotics Suite, we asked a panda robot arm to push block with different mass distributions. Since the mass is not uniformly distributed across tasks, the robot needs to learn to maneuver the position of its end effector on the backside of the block to correct for orientational deviation when pushing the block forward. Here, we show the episodic reward evaluated during training. HyperCRL outperforms other continual learning baselines like synaptic intelligence, elastic weight consolidation, and course set. The average performance of our method is on par with the multitask learning baseline, which has access to the entire history of data. On the other hand, simple fine-tuning catastrophically forgets and is unable to perform pushing for all 5 types of block at the end. The next task involves pushing a block, which in turn kicks the second block towards a goal. We vary the friction of the second block across tasks, and the robot arm must adjust its push accordingly. Here are some of the sample results from HyperCRL after training on all tasks. In the last experiment, the robot must learn to open different doors, pulley handles, round knobs, and lever handles. Unlike the earlier examples, the dynamic switches here are much more discontinuous. We demonstrate the flexibility of HyperCRL in modeling very different task dynamics. The panda arm has to learn to use different motions to unlock the doorknobs and open the door. Here, we show the reward curve normalized with respect to a model trained from scratch separately on each task. While most continual learning baselines fail to retain knowledge of past tasks after training on new ones, HyperCRL successfully retains most knowledge and virtually sees no performance degradation. Of course, our method still has some limitations. First, the task boundary needs to be known in training so that HyperCRL knows when to save the snapshot of the hypernetwork weights. Also, the size of our hypernetwork is usually much larger than the target network, since it directly outputs all the weights. Lastly, while HyperCRL can achieve great overall performance at the end of training, as well as retaining performance on previous tasks, there are no significant forward transfer to new tasks from existing knowledge learned in the past. Thank you for watching this video.